Thanks for the introduction. Good afternoon, everyone. I know you probably want to go to that coffee section, but just bear with me. I'll try to be quick. So I am the second author, Xueying. Let me quickly introduce myself. I'm Dr. Xueying. I actually got my PhD at Emirates from Cambridge, so it's like coming home for me. I'm now an assistant professor at Ajman University. For those who probably have no idea what this is. It's in the UAE, United Arab Emirates, very close to Dubai. I'm required to introduce my university because they founded this. We are top 400 QS university, very active in international collaboration in research. So if one day you do want to visit Dubai, just let me know. So the first author, Masoud, is a PhD student that I'm co-supervising. He is from Iran, and he's, because of the war and got the visa issue, he couldn't come. So I'm representing his work. Oh, good. Let's go. So the introduction, the background of this is about concrete infrastructures. We're talking about transportation infrastructures, including bridges and highways made of concrete. So the concrete infrastructures is in general facing a challenge, which is aging issues. That could be spalling or rebar corrosion or whatever it is. So to address this issue, nowadays a very popular way to address this issue is to use the UHPC, which is called ultra high performance concrete, as the golden standard. However, we got another thing here is once you got something done with the ultra high performance concrete, you do need to monitor the structural health of it as the years passing by. But there is a gap in it. So traditional, how we monitor the structural health of that is we use traditional sensors. That includes something like strain gauges or fiber optic. However, these traditional ways facing a lot of issues, which includes very short lives, and once it's damaged, it's expensive or it's difficult to repair it, especially when, imagine you have a bridge and you got some strain gauges under the bridge deck, that location would be very challenging to be repaired. So what we say now is we propose something called self-sensing concrete. Self-sensing. How do we achieve that? We make concrete self-sensible. We make concrete electrical conductive. That requires us to make something that is electrical conductive into the concrete mix. So in this research, we use milled carbon fibers and also the steel fibers. I'm going to come into that later. So here is the mixing procedure. I want you to notice that. So instead of pure just cement, which is very high in carbon footprint, we also mix something GGBS and silica film. And also we use something called PLC, which is limestone induced. For those who is not familiar with concrete, those are all much, much lower in carbon footprint than the cement traditional one. So for GGBS, it's like tens in times of lower in carbon footprint. For limestone, that could be hundreds times lower. So even you include just like 10% or 15%, that's a huge change in terms of carbon footprint reduction. So low carbon. And then we use milled carbon fiber. Milled is the key word here. Instead of traditional commercialized carbon fiber, which is again not low carbon at all, we use milled carbon fiber. That is a commercialization carbon fiber waste from the carbon fiber production manufacturer from from Boeing, BMW, wherever it produce carbon fiber. So again, low carbon. We mix milled carbon fiber into water, and then this is superplasticizer to reduce the to increase the workability, because these carbon fiber could be really small in particle size, which because of the van der Waals forces, it could make the concrete mix very dense and not fluidity. So we add superplasticizer to increase the workability, and then we mixed it, and then we introduce the carbon fiber, and then do a little bit mix again, and then until we achieve a consistency in the concrete matrix. This is the mixing details, and then we come into the materials proportions. This table gives us a clear summarize of the mix IDs. So of course, we're going to have a control samples where no fiber is included. And the first one is only 2% by volume of the total mix of the SF means steel fiber. Okay, so control ones with no fiber, only 2% steel fiber. And then we're going to have one more little thing, which is 0.1% carbon fiber. And then the final one is 2% steel fiber plus 0.5% carbon fiber. And that's all the other things. These are the material details of the steel fiber and milled carbon fiber and an SEM image of the milled carbon fiber. One thing here to notice is that because the milled carbon fiber is just in theory a waste from the manufacturers, so it is very cheap in price. Okay, so we want to test if it's self-sensible, if it is self-sensing. So what we do is we have a cube here, and we do a very typical self-sensing geometric, which is 4 probes. And then you give the outer 2 probes some electrical pressure, and you're measuring the electrical performance from the inner 2 probes. That's what we often do. And you put it into the middle of a compressive machine. You give it a bit of cyclic compressive loading, and then you're measuring the electrical behaviors of that small cube. And then the result we are really calculating or looking into is FCR, fractional change in resistivity. Okay, apart from that, we also did some mechanical performance testing, including a very typical compressive strength, flexural strength, and some other durability tests, including rapid chloride and half-cell potential corrosion. So here comes to the very interesting results. For compressive tests, so we are looking into this orange, which is 28-day strength. With more carbon fiber, it actually decreased, which is not unexpected. I'm going to explain it later. For the flexural strength, with more carbon fiber, it actually increased because those carbon fibers helps the crack bridging and load transfer. So that's a good thing. Flexural strength increased. And then we're looking into the self-sensing performance. From here to here, it's 0 carbon fiber and more and more. Okay, so it's very obvious, it's very noisy, and there is electrical signals shifting in that. That's slightly better, but still the shifting, that's the best. So we can see that the 2% carbon fiber, steel fiber plus 0.5% carbon fiber have formed a continuous conductive network, enabling reliable electromechanical sensing. So this is the rapid chloride permeability. One thing to know that these are all fiber-free, no steel fiber, no carbon fiber, because they are electrical conductive, which is not suitable for this test. So what we tested here is the OPC, which means the ordinary Portland cement. This is the PLC with the L here, meaning limestone. As I said, limestone is low carbon. So basically, the low carbon one actually performs better, which is, again, a good thing. So it's not suitable for fiber reinforced, so we didn't test that. But the dense, ultra-high performance still provides excellent chloride resistance. They are all about this. Next is the sulfate resistance. For sulfate resistance, we tested the flexural strength after 28 days after it has been exposed in sulfate solutions. So these are orange data is after the exposure. And lime water curing, you can consider that as a normal curing. So there is a decrease after sulfate exposure, which is expected. However, the one with the most carbon fiber have the least reduction, which is again very good. So the 0.5 carbon fiber samples have improved crack bridging again and microstructure integrity, and therefore the least reduction in sulfate resistance. This is the last thing, which is the half-cell corrosion potential. From the top to bottom, so the top ones, which is the best performing ones, are just OPC and PLC ultra-high performance concrete without any fibers. These two middle ones are with 2% steel fiber and just a little bit of carbon fiber. The lowest one is this. Of course, the more carbon fiber, the lower it is. However, it is not because it's here. It's not compromised the corrosion resistance. It shows more negative because of the conductivity, because it has been more conductive, not the steel corrosion. And this line is, for those who don't know what this is, ASTM is American standard of concrete American standard. So the standard says above here there's no corrosion, so all performed quite good as an ultra high performance concrete. Finally, we got some SEM images. Scanning electron microscopy, which is just give us a more closer look into how the matrix actually looks. So here is 2% steel fiber without carbon fiber, 0.1% carbon fiber, and the most carbon fiber. We can see that from here, it has the most pore, it's the most porosity. Okay, we suppose the previous theory of the least compressive strength. I'll jump that. I'll jump that too. No, this is a acknowledgement. Thanks Ajman University, thanks to Louisiana State. Okay, cool, thanks. So, the conclusion is that with 2% steel fiber and with that in particular low carbon concrete matrix, 0.5 carbon fiber can be identified as the optimum dosage. I know you have been thinking, well, you just tested 0.1, 0.5. Why is 0.5? There is actually a previous project we have done previously, and we did test different dosages, and 0.5 is the best. But it reduced compressive strength a little bit, but it increased the flexure strength. It did form a stable, repeatable, and highly sensitive self-sensing network, which is really good. Excellent durability. So this is a very, this mix have a high potential. So that's it. Thank you. And thank you.